Hello. So let us close today the part of the so-called the standard integrals with the two techniques of integrations. The first is very famous and it is very powerful, is the integration by parts. Sorry, here. Okay. So the title of this part is Integration by Parts. And the starting point is again a rule of derivation, and in particular the so-called rule of Leibniz. So right here, Leibniz rule, and we have that the derivative of a product is equal to fg prime is equal to f prime times g plus f times g prime. Okay, now integrating both sides, we have that here the integral of f prime g dx. So we integrate f prime g here, and then we move the other terms here. So this is equal to fg prime dx minus f g prime dx. And this is just an indefinite integral. So we search for primitives, and of course a primitive of fg prime is fg. And then here we remain with minus fg prime dx. Okay, so this is the formula of the integration by parts. So I highlight it in green in this way. And now it seems to be quite a stupid formula to write, because we start from an integral, we have to compute an integral, and we end up with an expression when there is another integral. But the strategy is that this formula has to be used when the integral that we end up with so the integral at the right hand side, fg prime dx, is much better, much easier than f prime g dx. And of course it depends on cases. It depends on the cases we are treating. And so let us look some examples, because it is much clearer when we directly compute. So the first example is the following. You have to compute the indefinite integral of x e to the x dx. Okay? Now, what you have to do here is to interpret the integrand, which is a product of two functions, in this way, f prime g. So this is just a matter of interpretation. You have to interpret one of these two functions as g and the other as f prime, or vice versa. But what is the best interpretation? The best interpretation is the one that ends up with an easier integral. So, and at the beginning one can proceed by chance, but one can try to reason in this way. If x is f, x here is taken to be f prime, then we want to integrate it. So we end up with x squared, which is worse than x. Vice versa, if x is taken as g, then we have to differentiate it, and it will disappear because x, after differentiation, becomes 1. So let us see it directly. So we choose g as x. So x will play the role of g in the formula, and e to the x will play the role of f prime. Then here we write f and g. F prime is e to the x, also f is e to the x, so x e to the x, where here x of course is g, and e to the x this time has to be interpreted as f, and then here minus again f, which is e to the x, and g prime, which is 1 dx. So here we end up with an integral which is much easier than this one, so we can go forward, and here we have x e to the x minus the integral of e to the x dx. So this is x e to the x minus e to the x plus c. And so we have solved it. So just a comment, here in the formula of the integration by part, there is no c to be written here because c is embodied in the symbol of indefinite integral. So don't worry if here there is no c. C is here. Okay. Vice versa, here we no longer have a symbol of indefinite integral, so we have to add a plus c here. So if you don't believe this formula, just verify. Remember, when you don't believe in the result of an integration, then just differentiate the result, and you must find the original integral. So verify. And so just differentiate x e to the x minus e to the x plus c, differentiate it, and this is x e to the x to be differentiated, and when you differentiate x to the x, e to the x remains the same, and here we have e to the x, then minus, e to the x, and of course these two terms cancel each other, and you find at the end x e to the x, which is exactly the function we started with. So this is correct. On the other hand, we can remark, a very important remark. So the choice of the factor that plays the role of g and of the factor f prime in the original integral is crucial. One must choose in such a way the resulting new integral turns out to be easier than the previous one. Okay, this is very important. And yes, let us verify here by rediscussing the example 1, but with the other choice. of f and g prime, sorry, of g and f prime. So now we compute the integral of x e to the x, where x is f prime and e to the x is g. So here we have this is x squared divided by 2 is f, and then we have again e to the x. Minus, the minus which is in the formula, then f, x squared over 2, and then g prime, which is again e to the x. And you see here that the second integral, the integral we end up with, this is more difficult than the original one. So here, the message is that if you make the wrong choice, it is possible then then you have to go back to the original integral, and let us discuss this as a second example. The second example here is the following. So you have x squared e to the x dx, and so we have to proceed as before. So you want to differentiate x squared because it becomes easier. The degree declines step by step, and you can integrate e to the x because it doesn't change. So you write here x squared and the integral of e to the x, which is e to the x, minus, and here we have 2x, which is the derivative of x squared, e to the x dx, and again x squared e to the x minus 2x e to the x dx. Okay? And now you apply exactly the same strategy as before. So proceed with another integration by part, and so let us do it again. X squared e to the x minus 2x e to the x, and then plus 2 this time, because the minus in the formula is multiplied by another minus 1 in front of the integral, and here you have e to the x dx. So the final result is x squared e to the x minus 2x e to the x plus 2 e to the x plus c. And this is the second example. Okay? So the message here, one can iterate the integration by parts. Then third example, which is another important example, and it is the integral of e to the x cosine of x dx. And now the problem here is that when you integrate or differentiate the exponential and the cosine, nothing really significant happens. There is no simplification, because cosine becomes a sine, which is the same order of difficulty. E to the x does not change at all. But there is a trick you can use, and it is the following. So first, you can choose to differentiate the cosine, and then here you have e to the x cosine of x, and then you can have here minus integral e to the x, and then the derivative of cosine of x, which is minus sine of x. So let me write it again. Here you have e to the x cosine of x plus e to the x sine of x dx. Then again operate by differentiation by part here, and again you want to differentiate the sign. So e to the x cosine of x plus e to the x sine of x minus e to the x cosine of x dx. And so one here can be quite desperate because we gained exactly the same integral here and here. So this procedure seems to be hopeless. But notice that here there is a sign, a minus sign, and here a plus sign. So we are not really in the same situation as before, because these two integrals don't cancel, vice versa, they sum each other. So just take the second integral, the integral to the right-hand side, bring it to the left-hand side, and so you have that this is 2 e to the x cosine x dx is equal to e to the x cosine x plus e to the x sine x, and then e to the x cosine x dx is equal to e to the x cosine x plus e to the x sine x divided by 2. Since here we no longer have any integral, let us explicitly write plus c. And we can verify if this trick of iterating integration by part and then summing up to integrals does not convince you. Just verify it. So e to the x cosine x plus e to the x sine of x divided by 2 plus c prime. This is 1/2 e to the x cosine x prime plus e to the x sine x prime, and then 1/2 e to the x cos x minus e to the x sine x plus e to the x sine x plus e to the x cos x. And so the two central terms cancel each other, so at the end you remain with 1/2 2 times e to the x cos x, so this is equal to e to the x cosine of x. Okay, and then we can do many other nice sorry for all this stuff. Integrals that can be easily computed by using integration by part. So first we have to integrate log x dx, and of course this seems to be quite difficult, but just interpret this as 1 times log x dx. This is x log x minus, because I1 is equal to x prime, so this is f prime. So this is x log x minus x And then the derivative of log x dx, this is x log x minus x divided by x dx. So this is 1, and so again you have x log x minus x plus c. Again, let me verify, because otherwise you don't believe. And so when you verify, you have to differentiate x log x minus x prime, and this is x divided by x plus log x minus 1, and this is of course log x. And perhaps the other example I want to give you is an example of definite integral, because of course by integration by part you can also compute definite integrals, and the integral here is the integral between 0 and 2 and integrate arctangent, and as before put here 1, and here you have x arctangent x as before, and now you write, this is already a part of the primitive, so just the usual straight line with here the extreme of integration, okay? And then minus integral between 0 and 2, and here you have x times the derivative of arctangent, which is 1 plus x squared dx. Okay. Now you can compute directly the result here, which is 2 arctangent of 2. And then in 0 there is no contribution, because here there is x. Now you have to integrate this guy here, and this is a rational function. As we will see in the next video, you can always integrate rational functions, but here the main point is that in this rational function you basically have a numerator, the derivative of the denominator. Not completely, but the missing term is just a factor 2. So if here you imagine to have a 2, which means that you have 1/2 here. Here, this 2x is just the derivative of 1 plus x squared prime. And so here you have 1/2 log of 1 plus x squared between 0 and 2. So you have 2 arctangent 2 minus 1/2 log of 5. Okay? Then you can find many examples. You will do them in exercise and so on, but now I want to go back to our not to go back, to treat more exhaustively the case of rational functions, but let us go to another video. Thank you very much.